let's get started on this last part of it. So the good news is if you're thinking about it sort of like long story short, the nice thing about talking about mixed ANOVAs is that you already know all the parts. We did between groups, we did repeated measures, and all the mixed ANOVA really does is just slap them together. One little caveat about the complexity of it, because just like with repeated measures, any new source of variability has its own error. It's the same with mixed ANOVAs. Anything that's completely between groups has its own error, has one error. And every other thing, if it has even one repeated measures component, it has a separate repeated measures error term. So it's just lots and lots of error terms everywhere. So we're going to focus primarily on the computer output, the applied side of this, and not spend a whole lot of time doing the regression and all that stuff, just because it becomes so ridiculously complex to do those things that the what you get out of it is not worth what you have to do to get it. And so it's the same thing with repeated measures. No, we're not going to spend a whole lot of time on those things. So mixed, you actually will hear sometimes, you hear people talk about mixed designs in a different way. I'm using the term mixed to refer to mixed between and within, or mixed randomized groups and repeated measures. Sometimes you'll hear people talk about mixed designs to refer to mixed fixed effects and random effects. Now, we have not got into the difference between fixed and random effects. Everything we talked about, it has been a fixed effect. And if you want to learn more about random effects, you'd have to sort of go beyond this course. So take something in multi-level modeling, random effects, regression, hierarchical linear modeling, and they do offer classes like that at UCLA. They're usually at the graduate level, however, but maybe they do offer it in the undergraduate. It's been a little while since I've been there. So we're going to talk about some types. When you go through the assumptions, it's really, we're going to quick blip on that because it's really just the assumptions for each model apply to that part of the model. The assumptions apply to repeated measures, apply to the repeated measures part. Assumptions apply to between groups, apply to the between groups part. Right? Everything sort of. So you have things like sphericity and things applying to the repeated measures components in a mixed design, and you have things like homogeneity of variance applying to the between groups. We're only going to talk about deviation approach. This, just to sort of break down where the effects are coming from and how you get them, what they are. I'll go quickly just through like higher order mixed designs so you can see just how complicated they get in terms of how many errors and effects get generated from it. And then we'll spend just a brief time talking about breaking down significant effects. And I didn't really include things like effect size and that kind of stuff in here because it's really the same thing. The effect size that applies to between groups is the same as it is here for the between groups part. It's almost like you're doing two separate analyses just combined into one for one overall error term. So it's almost like you got different things going on in different parts of the analysis. Okay? This is it's a very popular design, especially in psychology. We start thinking about like clinical trial kind of things where you got placebo versus treatment. Those kinds of designs are oftentimes done with a mixed design. Very hard to see that marker for some reason. Pre, post, and then follow up. Yes, I know it says FU. We have to be that. And you have, let's say you have a group of, 5 people or however many people, they all go through that. They all get pre-test, a post-test, a follow-up. And maybe there's some sort of intervention in here that you do to try to see if that changes things, right? That's a pretty common design. I look at repeated measures. And the question always comes up with this is if you get an effect, if people do change pre to post, was it really due to the intervention or was it due to just people naturally changing on their own? Oftentimes, what people will do, what they want to do with this kind of design is to add in, you have another set, 6, 7, 8 people that from pre to post, they get no intervention. Right? So at this point in time, they get no intervention when this group does. This ends up being the treatment group. This is their control group. And what that does is it helps to control for the effects of things like carryover or just the effects of time or maturation and other things. Because if the change from pre to post or from post to follow up is really due to something that's occurring inside the participant, like it's something like just testing or carryover or something, then you would see the same effect in the control group. And if this effect appears, the change from here to here, and does not appear here to here, you would get an interaction between treatment group and time that would tell you that there is an effect for the intervention. The intervention actually does work, right? So in this case, oftentimes when you're doing mixed ANOVAs. Mixed effects is actually refers to the random effects that I was talking about before. If you're doing a mixed ANOVA and you are doing this kind of design, you're actually usually looking for there to be an interaction. What you want to show is that groups do differ somehow across time. Usually that's because there's some kind of intervention versus a control or something. And so it's the intervention that usually is what you're targeting. That's what you're most interested in. So requires that you have at least one between groups IV and one within subjects or one repeated measures. This is the simplest, well, okay, if I take the follow-up out, so it's just pre and post, two groups. This is the simplest form of mixed ANOVA you can have. One between groups IV with two levels, and one repeated measures IV with two levels. Okay, so that's the simplest, is a 2x2 design. This is sometimes, every once in a while, that's funny, in the lecture before, I had it often called, I don't think it's often called, I think it's every once in a great while called a split plot design, which comes from agriculture, where they would take the same plot of land and they would split it, and then they would do different things to it to see if, fruit or vegetable or something would grow better based on the intervention, keeping the soil, using the soil, repeating the soil up so that you actually have some repeated measures and some between groups, different treatments. That's where the split plot comes from. It's the same kind of design. If you ever hear that phrase, it's really talking about a mixed ANOVA kind of format. Okay. In the simplest 2x2 design, you would have subjects randomly assigned to one of two groups, but each group would experience two conditions, two measurements, two time points. Just in this case, let's say you're studying for the GRE, or you're trying to see which course, like Kaplan versus Princeton or something, is better at teaching people for to do better on the GRE. So you got the GRE before the class, you take like a pre-test or something, or the practice test, take another practice test after. You got the two different groups, people assigned to them, and you can see if one group changes more than the other, and be able to look at the effect of these sort of courses on people over time. So that's the simplest 2x2. The advantages here is first, it allows generalization of the repeated measures over randomized groups levels, the randomized groups levels. What does that mean? If you find an effect, right? If you say, go back to here, if you find an effect where there's no interaction at all, no interaction happens, everyone does better after before, then you can sort of generalize that the effect that Kaplan has on GRE test scores is the same as Princeton. It generalizes. You're able to generalize the effect, the trend. So instead of just asking, just taking a course, just studying for the GRE or taking some kind of intervention, just generally work, this is specifically generalizing it to these two different ones. You can also do it to other ones and see if it actually does help. And it does generalize across multiples of these. If the interaction occurs where it's better for one than the other, then this generalization does not happen. In order to have generalization, you have to have no interaction. An interaction tells you that there actually is a limit on your ability to generalize the effect, right? Because an interaction says this effect only occurs at one level of the other IV. That limits your ability to generalize. Second, it has the advantage of reducing error the way that repeated measures designs do, right? Because we're seeing people more than once. We can look at their averages, and we can take that consistent scoring, consistent differences between the participants out of the error term and actually reduce the error. So our Fs end up being bigger. It doesn't do so as much as a purely repeated measures design, but it does actually help to reduce some of the error and help, potentially make the F test bigger. So it's increasing power. And I mentioned this already, but the disadvantage is that you're now taking the complexities that are in each of them, the assumptions, all that kind of stuff, and you're sort of adding them together. So now you're dealing with sphericity on one side with repeated measures, but you also have you're adding more subjects because there's between groups parts. You have to have homogeneity of variance. So you're having to meet different assumptions all at the same time because you're sort of mixing these two different approaches together. So this is what I mentioned a second ago, where we're looking at the types of mixed design. Other than any mixture of between groups IVs and any number of repeated measures IVs, there is what's called a pre-test, post-test mixed design to control for testing effects. So this is generically what it is. You got a treatment control, right, where this group gets a treatment in between pre-test and post-test. This group gets no treatment, and you're looking for an interaction specifically. You want to see that the treatment at the group that's getting treatment behaves differently from pre to post. It goes up significantly, it goes down significantly, or this group essentially stays the same. Or if this group does change, this group should change more, or in the opposite direction or something, right? And that's a way of sort of looking at, does treatment actually work above and beyond simple changes in people over time, or things like maturation, local history. There's all these different threats to validity that could explain why people move, unless you have this kind of group where you do this, where you actually split it up. So in terms of the general linear model with this is sort of the original factorial, where we have the mean of the population, and so we're always anchoring here because this is an ANOVA, so we're always saying everybody's coming from the same population, and it's these two IVs and their interaction that are moving people away from where they would normally be, which is right at their population mean. Plus, there's some random variability that separates people from one another randomly. It's just sort of individual differences, that kind of thing, just random variability that's outside of the interaction or either of the effects separately. So how does this work when we go to a mix? You notice there's a lot of letters here, okay? So just like with repeated measures, because subjects do repeat, we can actually identify subjects. Go back for a second. When we did this as a repeated measures design, let's do a generic one. If this thing, when you look at just the treatment group, we do this as a completely repeated measure design. We had these 5 subjects that repeated, so we got one sort of effect for subjects, right? So we can look at the average subject effect here, and this is sort of, but now we have that there's a subject effect in the treatment group, and there's also now a subject effect in the control group that could actually be different effects. The averages we get here may differ than the averages there. So we can't just look at one. So there's no more just one sum of squares per subject. We don't have that anymore. All right, sum of squares per subject gets sort of it gets modified because it's not just subjects, but it's the sum of squares for subjects that are sort of nested within that A effect. And it's the sum of squares for subject within A, because they're nesting within these A effects. So it goes back to that again. That's where that sort of this sort of subscript came from in the first place, right? Sum of squares for the subjects nested within A, which is sort of our typical error term that we would use. This is going to be like our between groups error term that we're going to use for anything between groups. And then what we're going to find is that we're going to have this interacting with other effects. So it's going to be like a weird mixture of between and repeated measures error terms, depending on what's going with what. And again, it's like there's even one repeated measures in the effect you're looking for, then you get the repeated measures error term. So instead of having in a one way or factorial repeated measures, it was like mu, alpha, and then s, and then there was a by s. This is the same thing where we're getting mu alpha, because alpha is the between groups effect. We also have subjects that are nested within alpha, this average subject effect within alpha, within that effect. Then we have the beta effect, which is the repeated measures effect. Then we have an interaction. Well, anything that contains B now is going to have a repeated measures error term. So it's instead of being like B by S, which is what we had in repeated measures, since S is nested with an A, it's B by S nested with an A. B by S with an A. All right, so you have this S with an A as deviation scores caused by consistent differences, right? This was a subject effect S before. We're just averaging over levels of A. And now we have this B by S within A deviation scores caused by interaction of that repeated measures effect and our subjects. Right? So it's the interaction of B with the subjects that are nested with an A. Right, so again we're messing around with things where the between groups effect just gets one error term. And because we only have one repeated measures, these two repeated measures effects, whether it includes A or not, get the same repeated measures error. So the analysis is going to look, you're going to have some kind of, generically, you're going to look like something like this. We're going to have, if this is how you're going to set it up, say, in a program like Jamovi or SPSS or something, you would do it this way because each subject now is a separate row. So because each subject is a separate row, we're going to look at the effect of the different randomized groups going this way, right? So you got these 5 subjects are in one group, these 5 are in another group, these 5 are in another group, and going across the columns is going to be the within groups the repeated measures part. So B1, B2, B3 is the repeated measures. This is the basic sort of setup and how this is often put into programs like SPSS or SAS or when you want to run a mixed ANOVA. So what are the sources of variance and degrees of freedom? So what between groups parts do we have? Just looking at this generically, what is completely between groups? What effect? Yes, A1, A2, and A3, that comparison is the only thing. So the effect for A, right, is the only thing that is between groups. It's going to have its degrees of freedom are going to be the number of levels of A minus 1. Pretty straightforward. We have 3 levels of A. There's going to be an A minus 1 degree of freedom. What else is completely between groups? Or is there anything else? Since our subjects sort of nest within A, we can sort of think of it, it's not really between groups, it is sort of comparing, it's between subjects sort of, but we can at least think about the subjects that are within A as at least being part of this between groups component. And that's going to be the levels of A times the number of subjects in each group minus 1. A times A minus 1 is going to be a degrees of freedom, which is the same thing as A n minus A. A times n, so there's 5 people in each group, times the 3, so that's 15 minus the number of levels of A, which is 3, so it's going to be 12 degrees of freedom for that. The reason I got this, the reason why I like writing the error term this way with the S with an A, is that just as a quick side note, if you're thinking about degrees of freedom, whatever's on this side, below this slash, you would then put on the outside of the parentheses. Outside of parentheses. Whatever then is up here, subjects, goes then on the inside minus 1. It's a way to sort of quickly figure out the degrees of freedom associated with this. A n minus A because of that. What are the repeated measures effects? The obvious one is which? Yeah. So our B effect is for sure our within groups or between, repeated measures effect. And then what may not be so obvious is anything that includes B is now going to also be repeated measures. So if we're getting an A by B interaction, considered repeated measures. It has our within groups component, so it's automatically that way. And because to get our repeated measures error term, it's always the levels of the IV times subjects. It's an interaction between them. We're going to have a B by S interaction, just like we do with all of the repeated measure stuff we did in the last lecture, last set of slides. But because S nests with an A still gets to be in there, which is why both B and A by B get this interaction. A is the only one to get this error term. So for B, it's pretty simple. I said B and I hand wrote A. B, it's 1. Here, because it's an interaction, we're going to multiply. A minus 1, B minus 1. Here, because again it's an interaction, we're going to multiply. So we're going to do B minus 1 times n minus 1. And then we're going to multiply that by A at the end. Because the A down here. We're going to get A times the B by S interaction. This ends up being like crazy. ABN, it's like ABN minus AB minus, second, I'm doing this the wrong way. So it's going to be BN minus B minus the S, the N, the N degree of freedom plus 1, but then you multiply A through there, so it's ABN minus AB minus AN degrees of freedom, AN plus A. You can multiply A through it. I'm just like doing FOIL on those. BN times minus B minus N, N is the S effect, whatever, minus N, and then plus 1, and then because A is on the outside, you multiply A through. That's the degrees of freedom for it, so it's become kind of crazy. This ends up being A B minus A minus B plus 1. All right, so imagine if we designed that, like example we used before, where we had like people reading books over months or something. That if you decided to have people, instead of everyone reads like science fiction and mystery for 3 months, why don't we break it up, or people get randomly assigned to either read mystery or science fiction, and then check in with them every month. So instead, we can actually have that happen. We can actually randomly assign it to 3 different books and have them read all for all 3 months. So we can actually have a mixed design where you have different genres of books over time like this. Okay. Then we have 5 people assigned to each type of book: romance, mystery, science fiction. All right, so we have, it's the exact same setup we just had, just now putting some context to it. You got the A effect type of novel or genre novel is the between groups. Month is the repeated measures. Got all kinds of crazy stuff. Case means, you got means for each A level, marginal means here. We got marginal means for each B level. We got means for each combination. A1, B1's 2.4, A1, B2's 3.8. We got lots and lots of stuff going on. So here's the interesting thing. Whenever you want to look at the between groups effect, the between groups part, we actually don't need the repeated measures component in there to look at the between groups part. All I really need is the 4.2, 2.8, 2.667. All right, so we said a second ago that we can break the variability down into these parts. The effects for A and S with an A. Those are two the between groups parts. And we got B, AB, and B by S with an A. So because B by S with an A and AB are interactions, we're going to address them by sort of subtraction like we did before with all the other interactions we've talked about so far. So this stuff gets scary quick, but let's sort of walk through it real fast. This looks like, oh my God, so many, this is like too many equations. You see 2 sets of brackets. You got one bracket here, you got one bracket there, because there's 2 different interactions. One, it's an error term. One, it's an effect we're interested in. But again, thinking about the dot notation helps a little bit to sort of in those placeholders. So you have three things going on. You got I, which is individuals. Let me write that down. Yeah. J is for the A levels, right? And then K is for the B levels. Right? So if I have I, J, K together, that means every individual in every combination of A and B. A1, B1, A1, B2, all that stuff, okay? This is every single score minus, and because it's dot, 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 I'm averaging over everything. Averaging over subjects, over A, over B. This is grand mean. This is, everything's averaged. Here, I'm averaging over I and K, but not J, which means I need to have one mean for each A group. This is my A means minus, again, the grand means. This is the effect of A. This is the between groups A effect. And then here, it's just the opposite. I'm averaging over I and J, but I need to have one mean for every level of B. I need B1, B2, B3, all those B's need to have its own average. And I'm weighting by the number of subjects in each of those as I subtract the grand mean out. Just gonna declare it, right? To get the interaction, I'm looking at here, I'm only averaging over individuals, but J and K are staying the same. So every combination of A and B should have its own mean. So I need a mean of A1, B1, a mean of A1, B2, a mean of, right, A1, B3, because every J and K, every level of A and level of B are present. I need one of those, so I'm only averaging over individuals. This is each of the cell means multiplied by its number in each cell, and subtracting out the effect for A, the effect for B, so that what's in the brackets is the interaction between A and B. This is the sum of squares between groups. This is every single, cell versus one another, as if it's a one-way ANOVA with 9 cells, and I'm subtracting out the effect for A and B to see if there's anything left. And the answer could be that there's not, that there is nothing left. That after we take out A and B, there's no variation between those cells, but anything that's in here then represents the interaction. We can test it to see if it's significant. Down here, I'm getting one average for every single person, every individual, every subject. It's getting its own mean because I'm going to average over the levels of A and the levels of B. Okay. And then here is, this is subtracting out the levels of this is all the A levels, around the A levels. And then this in the brackets, this is every individual minus their own cell mean, right? So I'm averaging over individuals, but leaving J and K. So this is each cell mean. So this is typically the within groups effect. So here we have the typical within groups. Here's our old between groups, within groups, and subtracting out the sum of squares for the S with an A that we just found here. And the in here is that B by S with an A. This is what that interaction is. See a hand. So going back over here. So again, you don't necessarily need to memorize all this stuff. I'm not that concerned about, you should be able to read this and know what it is and be able to understand that this means that I'm getting a mean for every level of A, because remember, J goes with the A level. So AJ, A1, A2, A3, I need to have one mean for every A level. Here I need to have one mean for every B level. And to get those means, well, how am I getting the means? Well, I'm averaging over individuals and averaging over the levels of the other IV, levels of A. And for the grand mean, it's like I'm averaging over everything. I average over B, average over A, and I average over subjects. Let's start breaking these down a little more clearer. This is like a different way of looking at it. So whenever we, comparing between to repeated to mixed, right? What you get is that when we first did this, we called this sum of squares within groups, right? But it's still the same thing. subjects within the A by B combinations. So this is just, we had one error because it was between A, B, and AB all got treated with the same one error. Because there's no repeated measures, we could do that. We moved to repeated, A, B, and AB were the same. We still found the effects for A, B, and AB exactly the same. That's the same thing for mixed. We're going to find those the same way. The only thing that was different was we found an additional error for subject and then looked at how each of those interacted with subjects. So the error for A is the sum of squares A by S. The error for B is the sum of squares B by S, and the error for the interaction is A by B by S. So this part, our error term blew up from one error term to 4 by simply moving from a between groups factorial to repeated measures factorial design. We got a lot more error. But the main take home here is that the way we find these three effects ends up being the same, regardless of how you're doing it. What differs is what error terms get computed and what error term goes with what effect when you're going to find your F value. So here, because A is the between the groups effect, it gets one error term, which is S with an A, subjects with an A. This is my between groups error term. Because both B and A by B contain the B repeated measures, they both get this interaction between B and the subjects with an A. So while this becomes a little bit easier, we went from one error term to 4. Now we're back to just 2. It's getting a little bit, this is a little better, but now you got to remember what things go with what. That both B and AB get this one, but A gets that one. Here, at least, it was like A gets A by S, B gets B by S, A by B gets A by B by S. It's like everything has its own error term and everything just goes with it. When you get to a mixed, this one error term now applies to both B and A by B because B is the repeated measures. In order to do A and S within A, we really don't need all this data. What it does really is, let's pretend for a second that we're doing a one-way ANOVA with just A. All right, so I'm like forgetting about all this stuff. I'm collapsing all this stuff down to just looking at the case means and the averages in each one of those. The only thing to keep in mind, though, is that this 3.333 is not a single response. It's not just a single thing that someone responded to. It's actually the average of these three scores. 1, 3, and 6 gives us this 3.333. So as long as you keep that in mind, that this really represents 3 scores, 3 scores, 3 scores, we can sort of do a one-way ANOVA and adjust a little bit for the fact that each one represents 3 scores. But we don't need all this anymore for A and S with an A. We can sort of collapse that down and not even do it anymore. Okay, that makes sense. So this is for A and S with an A. This is all we need to look at. Okay, so the only thing you notice here is that there's a K. So when I'm doing the mean of each subject, 3.333, 4.333, 4, 5. All these case means minus the group mean, 4.2 minus 2.8 minus 2.773. This is basically doing sum of squares within groups. All right, this is the sum of squares within groups we did before, where it looked like just the sum of each individual, individual minus the grand mean. Right? This is what we did before for like within groups. The only difference now is that we're just replacing this with the dot j dot. It's not sorry, because it's repeated measures. I'm sorry, this is because it's within groups. It's not the grand mean. This is supposed to be we just had it as j before. Each I score minus each j group. We just had one effect. We just had A. We're like, all right, we're just going to subtract out the mean of each group, each individual score, and then there was no weighting because we're doing it for every individual. So it simplified things out pretty easily. We just did one for everybody, squared it, added them all up. Well, now because we have another thing to think about, we need one of these. Look, we're going to average over actually, it's sort of funny because in order to get this mean for each I, I'm not averaging over. So I think I wrote this a little wrong. It actually should be dot j or ij dot, because I need one mean for each individual in each group. So I need a mean there, 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 there. But if I did it dot dot, I would then average over again. I don't need to average over a. I need to actually have both. This is actually, I think, a little wrong. It should be like something like y bar I j dot. This is literally me looking at my own notes and arguing with myself in front of you. So this is how I thought it should be before, and now I'm changing my mind for some reason. But and this is why this is dot j dot, because I need one for every a, averaging over the a, the I levels, the individuals, and the j. So we already averaged over b to get these. So if I just average over I get the 4.2. That's what's going to go here, the 2.8. And the only difference is that each one of these represents a k number of levels of b that we averaged over, so then needs to be brought back in there again. Remember I said that at the very beginning of this, it said, like, just keeps getting weirder. It does, because now this is even stranger. We're talking about individual means, and we're waiting in weird stuff, and we're getting error terms. It becomes sort of strange. It starts to become less natural feeling. That's become sort of forced in some way. Let's look at how, like, where these parts all come from. If I want to look at the effects for A, it's the same old, right? We just say, look, I want to take 4.2 minus the 3.244, right? I want to take 2.8 minus the 3.244. We're getting that difference. 2.733 minus that 3.244. The only confusing part is we're multiplying by 15. Why 15? Because when we look back here, that 4.2 that we found is really the average of these 15 scores. So 4.2, yes, it represents these 5 means, but those 5 means are also representing 3 scores. 3 times 5 would be 15 scores to get this 4.2. The thing you gotta keep track of with this is that there's extra levels that we're still collapsing over. That's why we're multiplying here by 15. When it says nj, you expect it to be 5. If this is sort of one-way ANOVA. But it really isn't. It's 3 times 5, which is why it's 15, and all that stuff. And you can see what I mean by this I dot dot not making any sense, because there should be one of them for every person in every A level. So I'm not averaging over A here, so it should be ij dot and subtracting out the dot j dot, which is the averages. So we're talking about 3.333 minus 4.2. It's there. This is all like the within groups. 4.333 minus 4.2, 4.4 minus 4.2, 5.667, which is there, minus 4.2, 3.667 is there. All right, so it's just everybody in the first group all around their own group mean. Second group, 1.333 around its group mean of 2.8. All right, 3.333 minus 2.8. Again, 3.333 minus 2.8, 2 minus 2.8, 4 minus 2.8. That's everybody in this first group. Obviously, we're squaring, we're sort of adding up as we go. Then we got the 2, the 3, 3, 3, and the 2.667. 2, 3, 3, 3, 2.67. That's every single score or case mean that we had. And normally, because this is like an error term, that'd be it. We just add them up and be done. But because each of these scores represents 3 scores, we have to multiply by 3. It's that k level here to actually sum it all up. So we get that that sum of squares for S with an A is 26.4, or for A it's 20.583. Sort of, you can stop me if you have questions. Just going through it so we can actually get through all this stuff. Now you have, so now we're away from A and S with an A, we can actually look at the whole thing. Go back to here again. So I want to do the levels. So B will make a little more sense. It's kind of hard to look at with A because you're collapsing over, but for B, the reason why like it's NK and it ends up being 15 is because how many people are in A1? A1, 1 month is 15 scores. These 5, right? Those 5 and those 5. So it makes sense that we would weight this by 15 because that 3.333 is the average of 15 scores. So 3.333 minus the grand mean. Again, 3.333 minus the grand mean, 3.067 minus the grand mean, all those, then look at the effective A, which is really, really small. So only got 0.708 sum squared. To get the interaction, we're going to look at everything that's inside. This is now going to get messy. It's going to be every single cell around the grand mean. So we got 2.4, 3.8, 6.4, 4, 3, 1.4, 3.6, 3.2, 1.4, all subtracting out the grand mean and squaring it. That's going to be everything that's here. And in each group, that 2.4 is the average of 5 scores. So I'm going to multiply this by 5. We follow that through. You got the 2.4, right? The 3.8, the 6.4 there, 4, 3 there, 1.4 is there, 3.6 there, 3.2, 1.4, right? All subtracting out the same grand mean over and over again. Multiplying by 5, because each one of those means in there represents 5 scores. 5 times all that. Now, when I get that, all this 92.711 is the sum of squares between groups. It's not the interaction. It's just the sum of squares between groups. To get the interaction alone, I need to take the effective A and the effective B out of it. So subtract out the effective A, subtract out the effective B that we just found already, and we get that the interaction is 71.42. This, we're going to do the traditional old school sum of squares within groups. That's every single subject. 1 minus 2.4. 1 minus 2.4. 3 minus 2.4. 5 minus 2.4. 2, 2.4. We're going to do that 5, 10, 15, 20, 25, 30, 35, 40, 45 times. 45 subtractions and squares. It's our within cells sum of squares. And once we find that, we're going to subtract out the sum of squares S with an A we already found. And that's going to give us our repeated measures every term of B by S with an A. Let's look at all those. Look at all those numbers. Right? Where are those numbers coming from? Look at the first line. First line's all from the science fiction at 1 month. 1, 1, 3, 5, 2. 1, 1, 3, 5, 2. And subtracting out its cell mean. I'm averaging over individuals, but I need 1 for every cell. So I need its cell mean. So that's why I'm subtracting out 2.4, 2.4, 2.4, 2.4, 2.4. But now when I change to the next group, I have a new mean, 3.8. So now I'm doing 3, 4, 3, 5, 4, 3, 4, 3, 5, 4, minus 3.8, 3.8, 3.8. All right, subtracting this out. Everybody next group, 68675, 68675. I'm subtracting out this mean. The next group, I'm subtracting out that mean because they're all in this cell, the mystery 1 month. The next one, I'm subtracting out this one, the mystery at 2 months. Next one, I'm subtracting out this one, which is 1.4, which is the mystery at 3 months. Then I'm switching again to down here, romance, 1 month. All right? Romance, 2 months. Romance, 3 months. So I'm just subtracting. So this is just within groups. If this were a completely between groups ANOVA, this would end up being our sum of squares within groups. This would be our error term, just one error term. That's it. We just have this one. But because we were able to identify some consistent scoring back here with the S with an A, that was, we identified there was some consistent scoring using their means here with the S with an A. So I can't leave that alone. I can't pretend like that's just random now. I can't just leave it in here because that exists in here. But I already found it, that's 26.4. So I'm going to take and subtract those two. And this is now my my repeated measures error term at 37.2, because it's the interaction between time, month in this case, and that between groups error term that we found a second ago. Totals found exactly the same way. We can pretend like it doesn't matter if it's between, within, whatever. Total is the same. What is the deviation between every single score and the grand mean? So we're doing that 45 times. Every single score. 1, 1, 3, 5, 2, 3, 4, 3, 5, 4, 6, 8, 6, 7, 5. All those, all just subtracting out the grand mean all the way through all 45 individual participant scores. Okay. we get to the total is 156.311, and everything should add up. A, S with an A, B, AB, B by S with an A, all those should all add up this 156.311. And if everything is done correctly. And we had talked about our degrees of freedom already, but A has 3 levels, so it has 2 degrees of freedom. We multiply 3 levels of A times the S minus 1, the 5 minus 1, you get 12. B also has 3 levels, minus 1 is 2. Interaction, just multiplying 2 times 2 gives you 4. And then here we got our interaction between S and B. So 2 times 4 is 8. But then you're multiplying it by A, which is 3, which is why you get 24. And then this is our A times B times S, so 3 times 3 times 5. This is our 45 minus 1 is 44. Okay. So I just put them all in here, all the sum of squares that we found and the degrees of freedom. But the important thing is sort of see how this lines up. A goes with S with an A. Those two go together. We can divide those two and get an F. That part's easy. It's all because it's all between groups. We can use that one error term and be done. B and A by B, these two get this error term, this 1.550, so you get each one of these, dividing it by this one to get these 2 F's. And everything should add up to total. So we add up those 2 plus these 3, it should get the total. It does. It works out. All degrees of freedom should add up together as well. And we have these 3 effects that we can report. Just like in any factorial design, we got the effect of A, B, and A by B. It's just where we get the error. What we're using as our metric for error changes depending on where we're, what kind of effect it is. So what we just did right now is just a 2A. 1 randomized group, 1 repeated measure. That's what this is right here. So you got a 2-way mixed. 1 randomized group, 1 repeated measure. A is a randomized group effect. You get 2 repeated measures effect because they both have B in them. And then you get 1 between groups error, 1 repeated measures error. All right, so far so good. Now imagine you have a 3-way ANOVA, which is A, B, and C. A, B are randomized. So that's the first example is A and B are randomized, C is repeated measures. That's actually the easy version. Because A and B are randomized, everything that's A, B, or A by B gets 1 error term. That's pretty easy. So the effect of A, B, and the interaction all get S within A, B. Because now all the solution nesting within combinations of A and B, because A and B are both between groups. Everything that has C in it, even just 1 C in there somewhere, gets its own error term. So C, A by C, B by C, A by B by C, all get this C times S with an AB. That's actually the easy one. That's the easy of the 3-way mixed. Because if you just move B over to repeated measures, so the A is randomized groups, between groups, B and C in our repeated measures, it gets a whole hell of a lot uglier. Because A is the only thing that's between groups, it gets its own S with an A, and that's it. Anything that has just B in it, along with A, gets, so B, A times B, gets a B by S with an A. Anything that has just C and or A gets its own error term. So C and A by C gets C by S with an A. And then everything that has both B and C, whether with or without A, gets a separate error term. Because B by C, A by B by C, get B by C by S with an A. You see how this ridiculous this stuff starts getting after a while? Let's do the last one, because this one's nuttier. You got 4-way, four IVs. A and B are randomized groups. C and D are repeated measures. If you look up here, the 3-way, we have A and B together. It looks exactly the same. A by B gets S and AB, because in terms of the randomized groups part, these 2 analyses are the same. This 4-way with A and B here, and the 3-way with A and B there, are treating the randomized group part exactly the same. It makes no difference, because it's randomized groups, it gets treated the same, that's why it gets the same error term. Same effects, same error term. So now you got it. So anything that's either C or C with A or B, that's one error term. So C, A by C, B by C, A by B by C, all get C by S with an AB. Anything that is D or D along with A and or B gets a separate error term. So D, AD, BD, A by B by D, all get D by S with an AB. And then last but not least, anything that's a combination of both C and E along with either A and or B, it gets a separate, an extra error term. So C by D, A by C by D, B by C by D, A by B by C by D, which is a four-way interaction, all get C by D by S with an A error term. It just gets nuts. Nuts. All right, running out of time here. So if you're trying to break down significant effects, anytime you get a significant effect, you gotta break it down. You gotta find out where the effects are. So if you have significant main effect, you're gonna do, if it's between groups, just treat it just like you always do between groups. You can do whatever you want. You can break down, you can compare things, you can do Tukey tests, you can do Chaffet's, you can do plan comparisons. All the between groups comparison error terms are going to be the same. All between groups are going to have the same error terms, so it makes the comparisons pretty easy. Within groups, that's not true. Every time you go to do a within group comparison, you rearrange data, you try to do something to look at the within groups separately, you have to compute its own error term. So there's this FComp formula that we really didn't talk about, but every time a new F gets computed, just read it that way. Every time a new test gets computed, the data has to be rearranged in order to find that effect and its own error, because every time you do it, it has to have a different separate error. So you do an example of that. And that same example where let's say we found, actually we didn't, but let's say we found an effect from month, where month was significant. If month is significant and I want to compare, say, month 1 to month 3, the way I would do that is to drop month 1 from there completely and have a new data set where I now have these data sets alone, these data points alone. I've now redone the case means and everything else, and to make a whole new data set so I can figure out how month 1 and month 3 interact with subjects in order to get a new error term and a new effect for B. It's a pain in the butt. You have to redo it and redo an error term every single time you go to compare any of these together. That's why it's sort of working with the repeated measures components of this stuff ends up being harder. It's good because you reduce power and it's efficient, but mathematically it becomes much more pain in the butt. There's lots more things to keep track of, which is nice that the computer does it for us. I think most of us would probably screw it up trying to keep all that stuff in line. So what interactions? Purely between group interactions can be treated with simple effects. You can do anything you want. If it's between groups, treat it the exact same way as if any between groups. When they're purely within groups, you gotta do all kinds of rearranging, remixing. It's a giant pain in the butt. Leave it to the computer program. Tell it you want to do some comparisons, you want to do some stuff in Jamovi, like do some Tukey tests or whatever, and on the interaction, it'll do it for you, and it should control for all that stuff for you without having to just keep track of all kinds of crazy stuff. Just realize every time you do it, you're gonna have a new error term, a new analysis has to be done every single time just to get a new error term. Makes it kind of crazy. So I realized that was kind of fast, and I jammed through a lot of it at the end, but a lot of it just repeats. So I was trying to, I wanted to talk about mixed ANOVA because I think it's actually one of the more useful kinds of analyses. It gets used quite a lot, especially in psychology and social sciences, because we tend to like to randomly assign people to groups or conditions to test them, and we want to see if they change over time. So that kind of combination becomes very, very useful. So I thought, all right, if you're taking this class, you should get through at least all those things, get to see what a mixed design looks like, understand how it works, and then in lab we'll talk about how to interpret some of the output and find all those crazy error terms and how to sort of interpret it, look at all those things and make sure that we're finding the right stuff when we're looking at interactions between repeated and between groups and all that stuff. I know it's kind of quick, but I think it's enough to sort of get you started and give you at least an idea what it looks like. And we can see how it comes out a little bit in, because there's like 2 different designs in the lab we can go through and sort of see what it looks like.